Okay, so we're going to be continuing our talk on algorithms and complexity, specifically logarithms. It's the second video, by the way, with another proof. This one is going to be log. I don't know why I'm writing log with a capital L. Log b, right, is equal to log. It's supposed to be lowercase l. Log l, log a plus log b. So we just want to prove this identity. It's an identity we've known for logarithms for a long time. So again, same thing that we did in the previous video, and you can actually pause it right now and then try to do it for yourself. Yeah, you can just pause it. Okay, I'm continuing. So we're going to say z is equal to log ab, right? X is equal to log a, and then there y is equal to log b, like that, right? Okay, all well and good. What do? We put it in the exponent form. So 2 to the power z, we bring this 2 over here. 2 to the power z is equal to ab. 2 to the power x is equal to a. 2 to the power y is equal to b, right? Okay, so we have this like it is as this, right? So now what do? Well, 2 to the power z, we know that a is equal to 2 to the power x, so it's going to be 2 to the power x times 2 to the power y, which is then just going to be 2 to the power x plus y, which is 2 to the power z. So z is equal to x plus y, but what is z? Z is log z is equal to what is z is equal to log ab. This is equal to log a plus log b. We have that over there, and that's how we do this proof. It's very simple. And at first when I was doing this, I was like, okay, it makes sense, but again, it didn't make sense. Like, we're just coming, we already know this, so we're just moving from here to that. It's as if we're just playing around with these figures. I don't know why. It makes it a bit easier to remember, but also, I don't know, it was a bit just, I was wondering, say, what's the point? Because it looks so straightforward. But then, we're now going to do a more difficult proof. And please pay attention on this one. Took me most of the semester to understand what I was doing, and I'm surprised. I'm surprised I actually managed to solve it. But it is log x is less than x, right? For each and every do I take for each and everything? For each and every x that is greater than 0, right? So basically proving that log x is less than 1. Now, first time I tried doing this one, my brain was all over the place, lying to myself and all that. But then with mathematics, just slow down, relax, right? Breathe, then look at the question, read it twice. Here they want us to show out, okay, log x is less than x for each and every x in whatever. So what we assume is that, let's say we have some value p, right? Assume some p, right, which is of course greater than 0, right? So if we have p, this p is going to be less than some other value that we're just going to say x, which is going to be less than or equal to 2p, right? And then if we have another value y, right, this 2p is going to be less than y, which is less than or equal to 4p. This is just us trying to show that we can have these values can be separated, right? We can have some value here, but then we can have other values in between them and all that. Again, I'm surprised this one was something else. But then if we want to prove this, right, so we're taking this y, we're going to take this y and say, okay, if we have this log y, right, this log y, it's the same as us saying 1 plus log y over 2. What did this log y over 2 come from? Well, basically what we're saying is, if we say this is basically log y plus 1 minus 1, right? But then this one can be written as log y plus 1 minus log 2. Since this is base 2, so this cancels to a 1, which is why that we have that 1 over there. But then what we then end up having is this guy over here, this one over here, if we subtract it with this one, we're going to get log y over 2, which is what this over 2 has come from, right? So just a simple identity, just things that are important to know when you're solving these things, right? Now we know for a fact, right? We know for a fact that this is going to be, because we're assuming that this is true somehow, so this is going to be less than 1 plus 1 plus y over 2, right? This is going to be less than y plus 1 over 2, right? But then since this is like that, this can also be less than or equal to y over 2 plus y over 2, right? Again, it takes some time to wrap your head around this, just trust me. Just trust me on this. But then we know again that this is going to equal, right, this guy over here is equal to just y. We can just say less than or equal to y, right? But then since this y is the same as this one, right, which is greater than or equal to this one, but you know for a fact that this one is greater than this one, but then since this one is greater than this one, and then this one over here is greater than this one, it means that this one is going to be greater than this one, which is going to be greater than this one. So we can conclude that log y is less than y. Some things I just had to accept. So I've said this is how this goes. Trust me, I've spent some time, but if you have an explanation for this, please you can explain to me. But this is one of the few calculations that I was that I'd been doubting for most of the semester, and surprisingly this is how it goes, and this is the right answer. But yeah, you just have to slow down and then just understand how this is moving. But we're just playing around with the inequalities here to begin with. Right, so if you understand how these inequalities are working, then yeah, there really isn't anything that hard about it. Yeah, we're just joking for a bit. And then finally, for our last proof in this video, before I move on to something else, is going to be log a to the power b is equal to b log a, right? We're going to have that proof over there. How are we going to run this one? Well, I'm going to say let z equal log a to the b, and then x will then equal log a, right? So we know 2 to the power z is equal to a to the power b, right? But then we know for a fact that this one 2 to the power x is equal to a. We can replace this with the power x here, so we're going to have 2 to the power z is equal to 2 to the x b. So z is equal to xb. What is z? Z is this. What is x? X is that. So basically we're going to have log a b being equal to b log a, just like that, and yeah, we have done our proof. So for most proofs that you're going to find for logarithms, you're basically going to be approaching them in the same way. I think this is easy enough. We can move on to something a bit more interesting, which is series, right? You did them in mathematical induction, but this one we're going to be doing geometric series, which can be a bit more complex, but again, you just need to slow it down and you'll see the bigger picture. It's very easy.